Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help us out over here, and it also helps us reach others in need of assistance with these topics. So what we're going to be going over today is we're going to be looking at differential equations, and we're going to be looking at exact first order equations, and this will be our first part in this series. So we have this differential equation shown on the screen here. I'm not going to read all of it. You can see it. And we have to solve it given our boundary condition of y of 0 is equal to 2. So when dealing with a exact first order differential equation, you have to do a couple checks to make sure you're in fact dealing with that, not just given in the title. We know it's because it's given in the title, but when you're just given this expression, it's like, well, how do you know that off the start? Well, let's work on it and see how we can determine it's an exact first order differential equation and how to solve that first order differential equation. So when dealing with a possible exact first order, we are going to have to write it, or at least try to rearrange this portion in a version of m times dx plus n times dy is equal to 0. So let's rearrange all this and try to get something times dx and then something times dy all equal to 0. So rearranging everything here, so multiplying through by dx on the left side here, and then taking this entire right side and popping it over here, this is what we end up with. We have 3x to the 5th plus xy squared. All of that's going to be multiplied by the dx, plus taking all this to the left side, just rearranging the internal systems here. We would have our xy, or x squared, times y minus off 2y and all of that with the dy equal to 0. So what I have here is that I have it in this form where this is my m, this is my n. Now, sometimes when differential equations are oriented like this, you can separate the variables, but in this portion, we cannot separate the variables. We have too much intermixing going on here. So we cannot use that easier method. So let's compare with this portion right here, because once you have it in this form, you're going to have to look at partial derivatives here, because you're going to have to take the partial derivative of m with respect to y must be equal to the partial derivative of your n portion with respect to x. Make that an x. If this is true here, then you are in fact dealing with a exact first order differential equation. So step one, put it in this form. If you can separate variables, go for it. If you can't, this would be step number 2, is determining the partial derivatives of each little portion with respect to y and then respect to x. So my m would be the 3x to the 5th plus xy squared. The n would be x squared y minus off 2y. So let's go ahead and check our partial derivatives here. So the partial derivative of my m with respect to y would just be the partial derivative with respect to y of 3x to the 5th plus x times y squared. And since we are taking a partial derivative with respect to y, we are going to treat x as a constant here. So this first portion does not have anything with y. It is just 3x to the 5th. So that little first portion there becomes 0. And then my second one, we treat x as a constant, and we're only taking the derivative of y. So it'd be y squared. Taking the derivative of that would be plus 2xy. So essentially my m with taking the partial derivative with respect to y, we end up with 2xy. Alrighty, so let's go ahead and let's scroll down here and let's do the partial derivative of n with respect to x. So this will just be the partial derivative with respect to x of my x squared y minus off 2y. Once again, since we are looking at the derivative with respect to x, we are treating only x as our variable, everything else as a constant. So this first portion right here, we drop down the 2, so it'd be 2x, y is my constant. The second portion, there is no x in that portion of minus 2y, so it would just be minus 0. So we end up with 2xy. Well, what are they? They're 2xy each of these, so they are in fact equal to one another. So when you have this portion when you can rearrange into the Mdx plus Ndy equal to 0, and you take the partial derivatives of each of those with respect to the opposite variable, well, when they're equal to each other, you are dealing with an exact first order differential equation. So that is the very first part, is checking to make sure this is what you have going on. Now, it's kind of given away because it's in the title, but when you're just given an expression, you don't really know. So that's always the first couple things you want to do, is check to make sure you are dealing with that type of equation. So since we have this portion, we can move on to our third step here. And what we have going on here is that we have this G equation, which would be equal to, oh, if I can just rewrite it here, Mdx plus Ndy. So we would have dg, where g is an actual expression, an actual equation. Because that is equal to 0, we can say it's actually a constant value at this point, and we have this portion going on here. So we're going to use this third portion right here, this third expression, to find out what y equation makes all of this finally true. So this is the procedure in which you would do this after you check to make sure that you have an exact first order. So let's switch back to red real quick. So we are first going to integrate our g equation. Our partial derivative of that with respect to x must be equal to m, because m has the dx attached to it. So the partial derivative of g with respect to x would just be that m portion. So since m, I'm just going to rewrite this a little bit because instead of scrolling back and forth, since m is 3x to the 5th plus xy squared, we would have this portion be equal to, g is equal to the integration of my m dx. So it would be 3x to the 5th plus xy squared, all of that with the dx. And since g is its own expression, its own equation, we would have some type of constant function of y here, which I'm just going to write h of y. Technically, this is considered a constant, but since we are taking the partial derivative with respect to x, this whole constant may be an entire function or equation of the y variable. So we have to include it in here. So since we are taking the partial derivative here of g, we are going to treat everything with the y as a constant value here. So integrating this, so we're only going to be working with our x's here, y's just become constants. And if you want to rewrite it, you can rewrite it like this if you want to, where this is g is equal to the integration of 3x to the 5th dx plus pull out the y squared, since we're considering all y's constants, x dx plus h of y. So my g equation would then be, once we integrate this, we'd have 3 times 1/6 x to the 6th plus y squared times 1/2 x squared plus hy over here for that equation of h, or that function of h. So my g equation, and I'll try to make sure that I write g and y's differently. So we would have my g equation is equal to x to the power of 6 over 2 plus y squared times x, I wrote it too many times, times x squared over 2 plus my h of y. Alrighty, so let's scroll down here a little bit further. So now we have our g equation here, but what is this thing? That's the thing with differential equations. It's like, well, you have one equation that you have to find that will lead you to another partial function that you have to find, which will lead you to another function that you have to find. So now we're going to be working on finding what is this right here. What is my h of y? So in order to do that, we have to take the partial derivative of g with respect to y, thus treating x as if it were a constant. So before we were taking partial derivative of g with respect to x, treating y as a constant, now we're going to flip that. And we are going to do partial derivative of g with respect to y. So let's go ahead and do this here, where we would just have this x to the 6th over 2 plus y squared x squared over 2 plus my function here of y. So this would be equal to, remember, we're taking partial derivatives of y. So everything with x goes to 0. There's no constant there. It's all a constant. So 0 plus, keeping all x's as constants, we would have y, so y squared would become 2y. So the division of 2 here drops away, and it just becomes yx squared. And then we are going to have our partial derivative of h with respect to y. So essentially this boils down to, if we want to rearrange terms here a little bit, make it a little bit easier in the end, x squared times y plus our partial derivative of h with respect to y. So what we're going to do now, and the reason why we did this is for our next step, is that we are going to now set this expression right here equal to the n, because look what we did before. We set the partial derivative of g with respect to x equal to m. Well, setting the partial derivative of y, or partial derivative of g with respect to y, would be equal to n because of this equation right here, part number 3. All right, so let's go ahead and do that. So this right here, partial derivative of g with respect to y would be equal to n, just like the partial derivative of g with respect to x would be equal to m. All right, well, n from before is just x squared y minus 2y. So let's set these two equal to each other. So we have x squared y plus my partial derivative of h, partial derivative of y, or respect to y, is equal to x squared y minus 2y. Well, the x squared y's are going to cancel from each side, so I'm left with the partial derivative of h with respect to y is equal to minus 2y. Okay, so now that we just have the partial derivative of h with respect to y by itself, what we can do is that we can integrate both of these sides, and then we can get our constant, in quotes, our constants h function. So let's do that on another sheet here. So we are going to integrate the partial derivative of h is equal to the integration of minus 2y with that partial derivative of y. So this just becomes h is equal to minus y squared. So now I finally have my h equation. So now I can take that and plug that back into my original g equation, which was this. So it'd be g is equal to x squared over 2 plus x squared y squared over 2 minus y squared. So if we want to scroll back and see exactly where that came from, it was right here. And now we actually have that function h of y. So this is my g equation now. Well, if you remember back to the third step, we would have that g equation would be such that we would have our mdx plus the ndy, right? We scroll back to our very front here, bear with me. Right here, the step number 3. Well, no, don't delete that, please. All right. So since we have this going on here, well, and this would have to be equal to 0, that means that this portion right here is 0 for a differential equation. So whenever that happens, that means g has to be equal to a constant, since it has to be equal to 0. So what we're going to do is we're just going to replace g in this equation with a constant. So this would be c is equal to x squared over 2 plus x squared y squared over 2 minus y squared. So that was the whole point of doing this formation right here, because in the end, this g equation is just going to be equal to your constant c, and it'll always be that for an exact first order differential equation. So now what we can do is we can rearrange this in terms of y. So let's go ahead and start rearranging here. So let me scroll down just a bit. So rearranging, I'm going to have x to the power of 6 plus x squared y squared minus 2y squared is equal to 2 times my constant c. So I just went through and multiplied by 2. And then rearranging even further, I'm going to have x squared minus 2c is equal to y squared 2 minus x squared. Just flipping sides here, taking out y squared from both of these terms. And then finally getting y is equal to the square root of x to the power of 6 minus off 2 times my constant, all divided by 2 minus x squared. Well, we have boundary conditions. If we didn't have boundary conditions, this would be our answer. But we do have boundary conditions, and let's just do that work over here real quick. So our boundary conditions were such that we would have y of 0 is equal to 2. Thus, this means that the y would be equal to 2 when x is equal to 0. So let's go ahead and plug these in here. So we would have 2 for our y is equal to the square root of 0 to the 6th minus off 2 times my constant divided by 2 minus 0 squared. Well, this kind of becomes a little bit easier here because it becomes 2 is equal to the square root of minus 2 constant over 2. So this ends up being that 2 is equal to the square root of my minus constant. Well, if we just square each side, we have 4 is equal to my minus constant. Well, then my constant is equal to a minus 4 then. So let's go ahead and just fill in our exact y equation. Well, my exact y equation then would be y is equal to the square root of x squared minus off 2 times my constant, which is a minus 8. Well, minus with a minus becomes plus, so plus 8, and then 2 minus off x squared, and that would be my final answer. So that y equation satisfies the original differential equation. Well, with differential equations, and let me back up here, that would be the process that you would use for the exact first order. You have to check to make sure that you are an exact first order. Then you have to do that processes of taking the partial derivatives with respect to x and y, finding out what your g is, and then finding out what that h equation is, and then plugging everything back in and finding out, using your boundary conditions to find your constant, and finally your y equation. So you're always looking for a y equation in the end. Now, with differential equations, you can always check your answer if you're given boundary conditions. So let's go ahead and let's check to make sure that this y equation that I have here satisfies my overall starting differential equation. So we're going to just plug in y wherever it occurs, and we're going to have to make sure that the left side of the expression is equal to the right side of the expression. So let's go ahead and do this. Let me scroll down a little bit because usually, typically, the checks take a little bit longer than the actual solution format. So doing our check here, and we'll just leave it in blue. So our differential equation, I'll just rewrite it real quick, is our beginning expression was 3x to the 5th plus xy squared is equal to 2y minus x squared y times derivative of y with respect to x. So let's go ahead and let's plug in our y equation everywhere it occurs. So we would have 3x to the 5th plus x times the square root of x to the 6th plus 8 all over 2 minus x squared. And then that entire portion is squared for y is equal to 2 times our y, which is, once again, x to the 6th plus 8 all over 2 minus x squared. And then we're going to subtract off x squared times y once more, which is x to the 6th plus 8 all over 2x squared. That entire portion is square rooted. Oh, just gets so messy when you're writing all of this out. So close off the brackets there, and then we have our derivative of y with respect to x. So the derivative with respect to x of our y equation, which is the square root of x to the 6th plus 8 all over 2 minus x squared. Okay, so that's what we got there. So we have to make sure that this left side is equal to this right side for it to be true. So whenever you have the derivative, always try to target that first and work that first because that's usually the hardest part. The rest is just algebra once you get that taken care of. So let's take care of this derivative first here. So I'm going to rewrite this portion as d dx, and I'm just going to take the square root and take it to the half power here. So what I'm going to have is x to the 6th plus 8 all over 2 minus x squared, all of that to the 1/2 power. So what I'm going to use here to get this derivative going is I'm going to utilize the chain rule, and I'm going to have to use some substitution here. So I'm going to set my u variable equal to everything that is being taken to the half power. So that would be x to the 6th plus 8 all over 2 minus x squared. And then I'm going to set, well, let's just change up the variables here. We haven't used f yet. So we'll set f is equal to u to the 1/2 power. So u is inside here, and then f is just this entire function now. So I would have df dx is equal to df du times du dx. So I would have to find my derivatives here of df, du, and then du dx. So let's go ahead and work on that. So df du will just be the derivative with respect to u of u to the 1/2 power. That's a pretty easy one there. That is just 1/2 of u to the minus 1/2 power. Let's just go ahead and substitute in what u is actually here. So it's going to be 1/2 times x to the 6th plus 8 all over 2 minus x squared to the minus 1/2. Alrighty. So let's then work with our du dx. So du dx is going to be equal to the derivative of x to the 6th plus 8 all over 2 minus x squared. Well, with this one, we're going to have to use the quotient rule here. So it's a quotient rule wrapped within a chain rule, wrapped within a first order differential equation check. Yay, right? As I said, usually the checks take longer than the actual process of the solution. So we're going to use the quotient rule here. So what we're going to do is, let's see, what variables haven't I used yet? So sometimes you just run out of variables. So let's use p is equal to my my numerator portion. So that'd be x to the 6th plus 8. And then let's use r, we haven't used r yet, as 2 minus x squared for my denominator. So this portion right here, whenever you have this going on, it is going to be d dx. And essentially what you have is p over r. So this will be equal to r times dp dx. And then we're going to have minus p times dr dx all over r squared. All right. So we just have to find the derivative of p with respect to x here, and then the derivative of r with respect to x. And those are not hard derivatives to take. So let's just go ahead and just write this out here. So we would have r, which is 2 minus x squared, and then derivative of p with respect to x, well, that would just be 6 x to the 5th. 8 goes to 0, so we don't include it. And then we're going to have minus my p, which is minus x squared plus 8. And then the derivative of r with respect to x, which is just going to be minus 2x here. And then all of it over my r squared, which is 2 minus x squared squared. Alrighty, so that is just my portion for du dx here. So I'm going to have to take this entire thing in blue, plug it in right there, and this portion over here and plug it in for f. So we're going to take this portion, multiply it by that portion there. So let's plug everything back in here together. So we are going to end up with the derivative that we were originally finding. It's going to be 1/2 times x to the 6th plus 8 all over 2 minus x squared to the minus 1/2. All of that multiplied by this, which is 2 minus x squared times x to the 5th minus off x to the 6th plus 8 times minus 2x, all of that over 2 minus x squared squared. And that is only for the derivative portion right there. So I have to take what I just wrote below and multiply it by this entire portion here. So I'm actually going to need another page to write all this out. So let's plug back into that original right part of the equation. that we have going on here, or we'll just write the entire equation here, left and right side. So we have 3x squared, or actually 3x to the 5th, sorry. Right. Because you just have to make sure that you double check everything, because every now and then, yeah, it's 3x to the 5th. You gotta make sure that you get all your variables and powers right, because you could screw up one little thing and it messes up everything. Times, and we'll do a little bit of simplification here because this portion was squared with a square root, so it just disappears with the square and square root. So x to the 6 plus 8 over 2 minus x squared. That is my left side. And as you can see, the right side is what I'm going to have to really work on because it is rather long. So we did some rearranging here, and I'll explain it after I write it out. So minus 2, or 2 minus x squared, all of that multiplied by x to the 6th plus 8 over 2 minus x squared. All of that to the 1/2 power, just getting rid of the square roots and using 1/2 powers here. And then all of that multiplied by that entire large expression that I just wrote on the previous page for the derivative, which is 1/2 x to the 6 plus 8 all over 2 minus x squared to the 1/2 power, and then multiplied, or actually that's to the, yep, to the minus 1/2 power. Sorry, I don't think I wrote that correctly in the previous page. Yeah, I did, to the minus 1/2 power. As I said, make sure that you have all your powers and everything correctly. So much room for error here. So all of that multiplied by 2 minus x squared times x, or 6x to the 5th, and then subtracting off x to the 6 plus 8 times minus 2x, all of that over 2 minus x squared, squared, close off, close off. All right, so what we have going on here is this right through here. Since u to the n times u to the minus n just gives you u to the n over u to the n, gives you 1. Since we have 1/2 power of the same expression times a minus 1/2 power, this is essentially just boils down to 1, which makes it a lot nicer to deal with. So also note that we have this expression of 2 minus x squared over 2 minus x squared squared is essentially just 1 over 2 minus x squared. So realizing these relationships here, what we can do is we can rewrite this even further to the point where we would have 3x to the 5th plus x to the 7th plus 8x all over 2 minus x squared, just taking x through. And then working through everything here on this side where this becomes 1, multiplying through again, and everything working out here. I also took all these expressions and multiplied everything through, and you end up with 12 x to the 5th minus 4x to the 7th minus 16x, all divided by 2 times 2 minus x squared. So utilizing all of this going through here and multiplying everything through with each of these functions using this and this value here, this entire right side boils down to this portion right here. So as I said, a lot of algebra there. So let's multiply both sides by 2 minus x squared to get rid of this division here. So multiplying both sides by 2x squared, we end up with 3x to the 5th times 2 minus x squared plus x to the 7th plus 8x is equal to, just dividing by 2 then, we would have 6x to the 5th minus 2x to the 7th minus off 8x. Not exactly the same just yet, but let's multiply through on this right side here, and we end up with x, or 6x to the 5th minus 3x to the 7th plus x to the 7th plus 8x is equal to 6. X to the 5th minus off 2, x to the 7th minus off 8x, and we are super close here. Just take this right here, and we end up with 6x to the 5th minus 2x to the 7th plus 8x is equal to 6x to the 5th minus off 2x to the 7th minus off 8x. And holy moly, we finally made it. The left side is equal to the right side. So as I was saying earlier, as you can see, that sometimes the check at the end to make sure that you have the correct y equation is a little bit longer than the actual problem itself. So this would be how you would work a exact first order differential equation, with this being our answer right here. So that answer right there satisfies this expression. And as mentioned earlier at the start of the problem, dealing with an exact first order differential equation, you cannot use separation of variables. You have too much intermixing going on. So you want to make sure that you do step number one, form your expression in this form, check the partial derivatives of m and n. If they are equal, you are dealing with an exact first order differential equation, and then work with step number 3, finding out what that g equation is, and then finding out what your h equation is. So I hope this video was helpful, and if you want to see more problem solvers Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel, because all of that does help us out. Thank you for watching, and I hope you have a fantastic day.